Hi, welcome to Opinion Polls and Card Counting, the Hypergeometric distribution. So here we'll discuss the hypergeometric distribution. Let's suppose we have a population of n objects. These objects come in two different types. For most of this video, we'll think about a population of marbles, which come in two colors, green and purple. Let's denote the number of objects of the first type, say green, in the population as n1. Then the number of objects of the second type in the population is n minus n1. Now let's take a sample of m of the n objects. To do this, we randomly choose one of the n objects. Then, without putting the object back in the population, we randomly choose another object from the remaining n minus 1 objects in the population. We repeat this until we have chosen m objects. The question we're asking here is the following. What is the probability that our sample of m objects contains exactly k objects of the first type and exactly m minus k of the second type? The answer to this question is given by the hypergeometric distribution. For example, we could take a standard deck of 52 cards. Initially, 13 of the cards are hearts. Let's say we removed 10 cards from the deck. None of them were hearts. If we take 3 more cards out of the deck, what is the probability that exactly 2 of the 3 will be hearts? Or let's say you're part of an organization consisting of 117 people. The organization has to decide on some proposition. You decide to poll 30 members to see how many are in favor or against the proposition. Out of the whole organization, 63 are in favor of it and 54 are against. What is the probability that your poll of 30 members will also show that a majority are in favor? Both of these situations can be addressed using the hypergeometric distribution. Okay, so in this video, we'll use a handy result which is derived in the short video, A Tiny Bit of Combinatorics. That result is the following. N choose m equals n factorial over m factorial n minus m factorial. If you know what this expression means and how to derive it, then you have what you need for this video. If not, you might want to check out that video first. Okay, let's get started. Okay, so let's say we have n marbles in a box. G of them are green, and n minus g of them are purple. You randomly choose m marbles out of the box, leaving n minus m marbles in the box. What is the probability, P of k, that k of your m chosen marbles are green? So you choose a subset m of the n marbles in the box. First, let's ask, how many distinct subsets of m marbles are there? For example, for n equals 4 and m equals 2, there are 6 possibilities. If we numbered the marbles from 1 to 4, you could choose marbles 1 and 2, leaving marbles 3 and 4 in the box. Or you could choose marbles 1 and 3, leaving marbles 2 and 4 in the box, etc. In total, there are 6 combinations. Now, more generally, the number of distinct subsets of size m that can be drawn from n objects is n choose m. That's n factorial over m factorial n minus m factorial. So this was shown in the video, A Tiny Bit of Combinatorics. If this result is unclear, you might want to check that out. Okay, so next, as each of the marbles has an equal probability of being drawn, each of these subsets is equally likely to be chosen when you choose your M marbles. So to get P of k, we can take P of k equals the number of subsets of M marbles containing exactly k green marbles divided by the number of subsets of M marbles. Okay, so we have that relation from the previous slide. Now we already know that the number of subsets of M marbles is n choose M. But now we need to get the number of subsets of M marbles which contain exactly k green marbles and thus M minus k purple marbles. So how many distinct subsets of k green marbles are there that can be chosen out of the G green marbles in the box? And how many distinct subsets of M minus k purple marbles are there that can be chosen out of the N minus G purple marbles in the box? The number of subsets of M marbles with k green and M minus k purple marbles will be the product of these two numbers. Okay, so let's start with the number of distinct subsets of k green marbles we can choose out of the G green marbles in the box. Well, this is just G choose k, so that's G factorial over k factorial G minus k factorial. Similarly, the number of distinct subsets of M minus k purple marbles we can choose out of the N minus G purple marbles in the box is N minus G choose M minus k. Okay, so the number of distinct subsets of M marbles containing k green marbles and M minus k purple marbles is therefore G choose k times N minus G choose M minus k. And we've written that out in terms of all the factorials. Okay, now to get P of k, we divide this by the number of distinct subsets of M marbles. So that's N choose M. Okay, so we divide that by N choose M and we get our expression for P of k. This is called the hypergeometric distribution. Okay, now let's use this in a couple of quick examples. So let's say there are 10 marbles in a box. 7 are green and 3 are purple. You choose 5 marbles out of the box without looking. What is the probability that the 5 marbles you choose contain 2 green marbles and all 3 of the purple marbles? So here, N equals 10, G equals 7, M equals 5, and K equals 2. Let's insert these values into our equation. Okay, so inserting N equals 10, G equals 7, M equals 5, and K equals 2 into our expression for P of k, we get that P of 2 equals the following. So the G choose k became 7 choose 2. The N minus G choose M minus k became 3 choose 3. And in the denominator, N choose M became 10 choose 5. Okay, so now let's mathematically work all of that out. So the first term in the numerator, 7 choose 2, is equal to 7 times 6 over 2. The second term in the numerator, 3 choose 3, is just equal to 1. And in the denominator, some of the factors in the 10 factorial are canceled by one of the 5 factorials. And so when we work all of that out, we get that P of 2 is equal to about 8.3%. So there is an approximately 8.3% chance that you'll pick 2 green marbles and all 3 purple marbles. Now let's do an example about something other than marbles. Okay, so let's say you belong to a club and you're running for the position of president of the club. You are running against one opponent. Voting has just ended and 50 club members cast their votes, which are all put into a box to be counted. Unbeknownst to you, you will win the club presidency with 36 of the 50 votes. Your opponent will get 14 votes. Let's look at the first 3 votes to be tallied, which are chosen randomly out of the box. What is the probability that you get all 3 votes, 2 of the 3 votes, 1 of the 3 votes, or even none? Okay, so let's again look at our formula for P of k. Here, instead of choosing m out of n marbles, we're choosing 3 out of 50 votes. So we'll set m equals 3 and n equals 50. Also, instead of having g green marbles in a box, we have 36 votes for you in a box. So we set g equals 36. Now we can write down the formula for this case. So P of k is equal to 36 choose k times 50 minus 36 choose 3 minus k, all divided by 50 choose 3. Okay, and then we write each of those 3 factors in terms of factorials. Okay, so let's simplify that down slightly. We have a factor of 50 minus 36 factorial. That's just 14 factorial. And also, we have a factor of 50 minus 36 minus 3 minus k, all factorial. We can just write that as 11 plus k factorial. And finally, our denominator, which was 50 choose 3, that turns out to just be 19,600. Okay, so now let's evaluate this for k equals 0, 1, 2, and 3. Okay, so let's start with k equals 3. When substituting in k equals 3, we get 2 factors in the numerator. The first one is 36 choose 3, and the second one is 14 choose 0. When we work it all out, this equals approximately 36.4%. Okay, next, k equals 2. Here, those 2 factors are instead 36 choose 2 and 14 choose 1, and we get 45%. For the case k equals 1, we get 16.7%. And finally, for k equals 0, we get approximately 1.9%. Now note that p of 3 plus p of 2 plus p of 1 plus p of 0 equals 1, which must be the case as k must be observed to be 0, 1, 2, or 3. Okay, now let's do a quick summary. Let's say we have a population of n objects where n1 of them are of one type and n minus n1 of them are of another. Then we take a sample of m of these objects. What's the probability that this sample will consist of k objects of the first type and m minus k objects of the second? The answer to this question is the hypergeometric distribution. Here, we've derived the hypergeometric distribution and given a couple of quick examples.